So far in the theory part, we have seen that we can apply the concepts studied in the transmission lines can be applied to match the uh, load, right? So when I say we are trying to match the load, we are referring to one diagram that is something like, uh, okay, something like this. This is the voltage source, and every source is going to have its own resistance or impedance. Okay, and we are trying to connect the source to the load by using the transmission line. Now, let us say the source has a resistance Rs plus J times Xs, right? And the ZL, the load. So this is something like, okay, ZL is equal to, it can have RL minus JXL or something, right? So whenever we say that impedances are matched, right, for matched load, we are expecting the Rs plus J times Xs is equal to load RL minus JXL. So if this condition is satisfied, we can say that energy gets transferred from the source to the load, and that amount of energy getting transmitted is maximum, right? Efficient power transfer. This is the condition. Okay, right? But to in the theory section, we have seen that whenever we want to solve any problem related to this, there is a lot of calculations to be done. We have a lot of equations, right? And we need to there is a lot of calculation in general. Okay, right. But right, there is a easier method to uh, match this load, right? Whenever there is no matching, right? Like let me say that there is, see, for a transmission line, I have a Z naught, right? So that Z naught, wherever we try to connect, let us say maybe if at all there is no matching, I can use the stubs to, right, single stub, double stub, etc., to match, right? But to do that, we have to follow standard procedures. We have to use a lot of equations, and then only we will come till that point. That's what we have studied so far. But the easier method is to use what is called as a Smith chart, right? So what is a Smith chart? Smith chart actually, it's a plot consisting of a lot of interlaced circles. Okay, so I can write circular plot having many interlaced circles. Ultimately, we find a lot of circles, right? But it looks pretty complicated, right? So that if you look at the speech chart, it looks pretty much complicated to us. Normally, we don't even understand, right? What is it? Okay, how to identify, right? Again, you can see that various numbers written over there, right? On the x-axis, you see numbers, right? Again, on circles also we see many numbers, etc., right? So our first objective is to understand the Smith chart, right? Once we understand, everything becomes very easy for us, right? So to trace whatever is written over there and to mark a point on the Smith chart, we need to know the basics of the Smith chart. All right, so first objective is to look at that itself. All right. Now let us consider, I'll try to draw another diagram. This is something like we are trying to understand, right? What is there? What are the various circles plotted, right? Normally we see, right? This is just a rough diagram. I can see that there is a outer circle like this. Then you see that circle's radius keeps on reducing. You may have the circles like this. That's one thing, right? And in addition to that, we'll have another set of circles that actually originate from this. Okay, I'll change the color. So from this point, they are plotted like this. Okay, so you have another, actually this is a circle, only one portion of the circle is written. Actually, this is the complete circle, which we don't see. All right, we see only a portion of lines drawn like this. They are the main circles which we are looking at this. In addition to that, we have even other circles. Okay, we'll see that later. So what exactly, right, are the black circles? What exactly are the red circles we are seeing? We are trying to understand that in the first half today. Okay. So once we understand that, everything becomes clear and it will help us in identifying the requirements. What are the points we need to plot on these circles? Okay, we'll come to know only after we understand what are those circles. Okay, right. So let me start with the one diagram. Right, that is again the same thing which I have drawn so far, but it's in a slightly different way. Okay, so let me consider the transmission line itself for the explanation purpose. So we have a transmission line like this. Okay, on this side, let me say we have the impedance connected. So there is a ZL. Okay, and the transmission line has Z0. The parameters are already known to us, so I will not explain what are the parameters again. Right, so I know that a voltage will be incident on the load. Let me call that as V incident. Okay, and some portion again, we will never be solving any problem on Smith chart, and if there is if the load is matched, right? So obviously we are learning the Smith chart because we have the problems where the impedances are mismatched. Z0 is ZL are not matching. That means there is a reflection, so V reflected, it can be even current. Okay, I incident, I reflected, no problem. Now, so this is our scenario. All right, I have mismatched load. Whatever is incident, a portion of the incident voltage of the currents will be reflected. Okay, that means I can definitely write a reflection coefficient. Reflection coefficient, let's call that as gamma of the load. For every load value, you have a reflection value. So that is V reflected divided by V incident. You can even measure the gamma value using the current charge. Okay, but since the Z is a complex value, now if you remember, we can try to write this gamma L using another equation. Okay, gamma L is equal to load impedance minus the characteristic impedance divided by the load impedance plus this Z. It's a complex number. ZL is complex, so even the Z0 is can be complex also, but most of the time we try to make it a real value itself. But complex minus real divided by complex plus real is a complex number. So let's try to write that as gamma. It's a gamma value which is complex. I'll call it as a real part of the gamma plus J times the imaginary part of gamma. Okay. So in short, let's try to write it in the following notation. So the gamma L can be written as gamma R for real part plus J times gamma I. That is the imaginary part. Right? So as the impedances are complex, the reflection coefficient will also be complex. That's what is the concept I apply here. Okay. Now what we try to do here is that every value for simply in order to represent the numbers in a simplified fashion, right? Or in order to reduce the number of unknown parameters, we try to do what is called as a normalization. All right. So the normalization happens for any z can be normalized. So first let's go for that. Any z. Okay, I'll write a capital Z so that normalized can be written in a small letter. Any Z, it's any impedance uh, on the transmission line can be normalized. So normalized in the sense I had a capital Z, but I'm converting that into a small z. Small z is equal to, let me try to do the normalization with respect to the load. So how do you do? Divide that by the Z naught value. So you can see that ZL is equal to, we already have written that it is R plus J times X. I divide that by Z naught. So I actually get R by Z naught plus J times X by Z naught. So what we do, we try to write it in this way. Small z, which is the normalized impedance, is equal to, so I'll call this is small r plus J times small x. So small letters are normalized, capital letters are non-normalized. What is present actual value? Okay, so this is r plus J times x. Let's hold on to this. Now I see that the gamma L, which has the ZL plus minus Z naught by ZL plus Z naught, I can try to write that in the same fashion, right? I can try to write it in the same way, right? So this implies, let's try to write the reflection coefficient. The gamma L becomes equal to, as we know, we have written that this is equal to gamma real part plus J times the gamma imaginary part. Okay, so this is gamma I. Now let me try to write that. That is equal to, originally we had written ZL minus Z naught divided by the ZL plus Z naught. Okay, so but I am going to divide this by Z naught to what you call normalize. Okay, so that is ZL minus Z naught divided by Z naught numerator whole divided by ZL plus Z naught divided by Z naught. Okay, you divide both the numerator and as well as the denominator by Z naught. Now what happens? I know that ZL by Z naught, ZL is ZL by Z naught is what? It's a, I can call it as a small z. Okay, small z minus Z naught by Z naught is 1 divided by, once again, small z plus 1. But I know that small z is equal to real R part plus J times X part minus 1 divided by, it's a real part plus J times X part plus 1. Is it okay? Right. Now I understand that. I got it like this, but I know one more thing, right? So from this, I can even try to get it reversed. In the sense, I can try to write also, I can try to write as Z. What is Z? Z is equal to, it is normally R plus Jx, but I can try to write a Z in terms of gamma L. We actually have derived this in equation in our theory part. That is how to write the impedance in terms of the reflection coefficient. This is the equation. 1 plus reflection coefficient divided by 1 minus reflection coefficient. Okay, so I know that reflection coefficient itself is a complex number, so I can write it as 1 plus gamma R plus J times gamma L, or gamma I by mistake, sorry, it's an imaginary part, so imaginary part divided by 1 minus the real part of the reflection coefficient minus J times imaginary part of this. Okay, now if at all I want to calculate R, now let me say that I want to calculate the R part, right? So how do you calculate R now? So comparing this, I want to calculate what is R and what is X. So in order to do that, what is the option now? I have only one option, that is rationalizing this. correct? So rationalizing this means, right, left hand side is still r plus jx, right? Right hand side, I'll do the rationalization. So this implies, okay, let me write the left hand side once again. So this is r plus jx is equal to, let me write this. This is 1 plus gamma r plus j times gamma I divided by 1 minus gamma r, right? You see, this is a real part, minus j times gamma I. So in order to rationalize, multiply and divide by the complex conjugate of the denominator. That means I should multiply 1 minus gamma r plus j times gamma I to the numerator as well as the denominator. 1 minus gamma r plus j times gamma I. All right, so let us multiply. This is equal to, so I can multiply the 1 plus gamma r and 1 minus gamma r, that is a plus b into a minus b. I'm going to get 1 minus gamma r, 1 square minus gamma r square. You multiply this and this, a plus b into a minus b. So directly we write that. Then 1 plus r, I am multiplying with this part. Okay, so that is plus j times gamma I into 1 plus gamma r. Then I'll multiply this with this term, first term. Okay, so that is plus j times gamma I into 1 minus gamma r. Then j into j square is minus 1 into gamma I square, whole divided by, the denominator is 1 minus gamma r whole square. Okay, that is a square minus j square is minus 1, so that is a plus gamma I square. Okay, so now let me try to expand the numerator, then we'll do the same thing with the denominator as well. So this is 1 minus gamma r square plus j times gamma I, then plus j times gamma I gamma r plus j times gamma I minus j times gamma I gamma r minus gamma I square, all divided by, now this you can see that the first term in the denominator is a minus b whole square. So a square plus b square minus of 2 times a into b plus gamma I square. Okay, so now let me try to separate the real and the imaginary parts in the numerator. So that is equal to, I'm trying to write the real part. Okay, it's 1 minus gamma r square minus gamma I square. This is the real term. Okay, then I think we have, let me try to look at the numerator. Gamma I, yeah, you can see that this term will cancel. Okay, so this is plus j times 2 times gamma I whole divided by 1 minus gamma r square minus 2 times gamma r plus gamma I square. So I can see that on the left hand side I'm expecting r plus jx. So let me write that once again here below. So this implies the r plus jx which I am looking at. I'll separate the real and imaginary terms, and I write two terms now. So real part is 1 plus gamma r, it's 1 minus. So this is 1 minus gamma r square minus gamma I square divided by denominator. Okay, 1 minus gamma r square minus 2 times gamma r plus gamma I square. Then plus j times 2 times gamma I divided by the same denominator. 1 minus gamma r square minus 2 times gamma r plus gamma I square. Okay, so it's very clear now, right? From this equation, I can try to write the real R plus Z is equal to, this is Z, right? I'm trying to write impedance, but impedance has two values, real value and an imaginary value that corresponds to the either in, the reactance of the capacitor or an inductor, R plus or minus Jx. So since I'm writing plus Jx, I can assume that I'm trying to write the inductance. Okay. So therefore, R is equal to, R means a real part. So R is this thing. So therefore, R is equal to 1 minus gamma R square minus gamma I square divided by 1 minus gamma R square minus 2 times gamma R plus gamma I square. That's the real part. And the imaginary part can be equated to 2 times gamma I divided by 1 minus gamma R square uh, minus 2 times gamma R plus gamma I square. You understood? Okay, right. Now, we need to, let's try to let's try to look at the R equation. Okay, it's a normalized equation, and my intention is to convert this into some standard form. So I'll call this is say 1, and let me say this is 2. Okay, from 1 and 2 I'll try to get two different equations, so that equation 1 generates a set of circles, equation 2 generates another set of circles. You see, R is the resistance, X stands for the reactance. Okay, so actually this equation number 1 is a equation of a circle, but we are not able to distinguish, identify that this is the equation of a circle. I need to do slightly, I need to do little bit of more mathematics. I need to bring that. Okay, so from equation 1, let me write this equation 1, you cross multiply. Okay, so that is R into 1 minus gamma R square minus 2 times gamma R plus gamma I square is equal to, right hand side is the numerator of equation number 1, right hand side. So that is 1 minus gamma R square minus gamma I square. Okay, so let me multiply them, and then let me try to simplify that later. So that is R minus R times gamma R square minus 2 times R into gamma R plus R times gamma I square is equal to 1 minus gamma R square minus gamma I square. Okay, so I'll try to move all the gamma terms to the left hand side and the only term containing R to this side. So that means the gamma R square and gamma I square will go to the left hand side. Okay, so that means I can write gamma R square, then do I have 1 minus R, so gamma R square, okay, plus R times gamma R square minus 2R gamma R plus R times gamma I square plus gamma I square. It should be equal to, okay, let me just check. think I made a mistake. Yeah, you see here I have made a mistake. So this is plus. Okay. So this is 1 plus. So I think I carried away with the same error throughout. So let me correct. So this is 1 plus, this is 1 plus, 1 plus, 1 plus. So that means this is 1 plus, this is plus. So we have a right answer. Okay. So this is what I'm trying to write. So plus gamma I square equal to, on the right hand side I have 1, and this r which moves to the other side becomes minus r. Okay, 1 minus r. So in this, let me try to take out whatever I can take out. So I can try to take out a 1 plus r outside from the first term. So I'm left out with gamma r square. Okay, minus 2 times r gamma r. Here I can take r plus 1 into gamma I square equal to 1 minus r. All right, so let me try to modify this now. I'll try to divide everything by 1 plus. So that means gamma r square minus, so this is 2 times r divided by 1 plus r times gamma r plus what do I have? I'm dividing by r plus 1. So here I'm left with only gamma I square equal to 1 minus r by 1 plus r. Okay, so let me think what we can do now. All right, so I'll add and subtract a term to the left side just to uh, convert this into a proper square. Okay, so I have gamma r square minus 2r divided by 1 plus r into gamma r. This is as it is, but I'm trying to add a term to this now. So this is plus r square divided by, I'm trying to write a r plus 1 here. Okay, r square by r plus 1 square. Then I have plus gamma I square. Then I subtract the term which I added. Okay, r square by r plus 1 the whole square, right, equal to, let me write 1 minus r by 1 plus r. Okay, now you see what we are trying to do here. So on the left hand side, I have, you see this whole part is going to generate a perfect square. Okay, a square minus 2ab plus b square, right? That I can write it as a minus b whole square. What is a? A is gamma r. Gamma r minus, see, this is r by r plus 1 the whole square. This is a, right? First thing. Then I try to uh, keep this term as it is. So plus gamma I square. I'll keep this on one side. Everything I'll try to move it to the other side, right? So on the other side, I have 1 minus r by 1 plus r, first term. Then I have the minus of r square goes to other side as plus r square divided by r plus 1 the whole square. Okay, those are the terms which I move to the other side. So now let me calculate this. So this is nothing but, can we simplify this further? Yes, I guess. So let me take the r plus 1 whole square in the denominator. Numerator becomes 1 plus r into 1 minus r, 1 minus r square plus r square. r square cancel. So this is simply 1 by r plus 1 the whole square, right? So that means I'll rewrite the equation what we got so far. This is gamma r minus r by r plus 1 the whole square plus gamma I square is equal to 1 divided by r plus 1 square. Is it okay? Now let me try to compare this with what we already have studied in analytical geometry, maybe basics of mathematics, okay, maybe in PU level or something, right? So this is the equation we know, x minus a the whole square plus y minus b the whole square equal to r square, right? What is this? This is a equation of circle. What is the detail? What other detail we get from this? From this, we also will come to know that the center, okay, centered at a comma b, and what is the radius? Radius is r, correct? So this is, I'll call this is equation number, say, 3, and this is what I'm going to call as equation number 4. So comparing 3 and 4, 3 should be equal to 4 according to me, because I can see the same notation, right? What is a value? A is equal to r by r plus 1, and b value is 0. There is no y minus b, right? So because I'm able to see that x is equal to gamma r, y is equal to gamma I, okay? In my reflection coefficient, are you understanding, right? Gamma is a reflection coefficient, correct? In the gamma reflection coefficient, real part of the reflection coefficient, I am going to mark along the x-axis, okay? And the same, very similar idea, right? The gamma I is my y-axis. Along the y-axis, I'm right. Using these two, I am able to write circles, right? Using the equation number 3, right? So the what is the radius, right? R becomes equal to radius of the circle will be 1 divided by r plus 1. Where what is this r? This r is my normalized resistance, correct? Because you see my impedance z is equal to r plus jx, correct? So use that resistance part and you will be able to write the circles according to this. Okay, now let's try to write this. Let's try to calculate the radius of various types of circles. Okay, now tell me what happens if the say a resistance is 0. When resistance is 0, what should be the radius of circle? Right? So capital R becomes equal to 1. And what should be the center? Center of the circle. It's A comma B. 1 comma 0. Just try put R is equal to 0. Now a small letter r equal to 0 implies A comma B equals to, it's 0 comma 0, right? A comma B, 0 comma B. So you see, understand one point, right? This actually creates a constant R circle. Okay, we call these uh, circles as constant R circles, and constant R circles have a feature that they lie on the x-axis only, because see, no height. The second component is 0, means no y-axis. All are along the x-axis only. Centers of these circles are along the x-axis. Okay, what is your x-axis? The gamma r axis. Okay, every point lies on this. Okay, so anyway, let's come to that. What is r? Capital R is equal to, what is the radius? 1 divided by 0 plus 1, so that is equal to 1. Okay, Fine. Now let's go to the extreme. Say r is equal to infinity. What happens to a comma b? What happens to a when you put r as infinity? Not defined, but I think you should remember one technique. If whenever it is, see, if I substitute r as infinity directly, it becomes infinity by infinity. That is undefined. But whenever some terms goes to infinity, you should do this technique. So r by r plus 1 is my equation. I'll try to take r common from the denominator. So this is 1 by, 1 plus 1 by r. Correct? So this r cancels. Now you put r as infinity. So that is 1, right? So when r is infinity, this is 1 comma 0. So I know that these are the extreme points, correct? Resistance 0 is a short circuit. Resistance is infinity is open circuit. So always you will have the values of the resistances that you might get for a given load lines. The values lie between these two. So now you calculate what should be the radius. Therefore, r is equal. In this case, 1 divided by infinity, 1 by infinity is 0. Correct? So first case, short circuit is represented by a circle centered at 0, comma 0 with radius equal to 1. Okay? And as the resistance goes to infinity, right, I am going to get a circle located whose center is 1, comma 0 with no radius. In the sense, it is just a point. Okay? So now I'll show you one diagram. So now you understand what do I mean by this. The whole concept can simply be explained by this one diagram. Okay, I'll directly copy and paste it so that I don't have to draw that. Okay, now, so this concept I just explained can be visualized by this one simple graph. All right, I'll show you this graph completely now. Let's see this. Right, this is what we try to the equation which we have written now, the equation of all set of circles, they can be represented by this one diagram. You see the extreme points are there. R equal to 0 is the outermost circle which you see here. Okay, and r is equal to infinity is the one which is a single point over here. You can see that there is a point here, right? Over here I can find a point. That point itself is, you see the measure, you try to represent that. X-axis is 1, height is 0. So 1 comma 0, you can see that 1 comma 0. Right? That 1 comma 0 is what we have represented over there. Okay, so with a fixed, now let's go for the midpoint. Let me say resistance is equal to 1. Okay, let me say R equal to 1. What happens to A comma B? Can you tell me? Can you calculate? I'll show you the equation. Please calculate. When R is equal to 1, A is equal to half, right? 0.5 comma 0. And what is the radius? Capital R is equal to half. So the meaning is that whenever you say that my resistance is equal to 1, I am supposed to consider that circle whose center is 0 0.5 comma 0 and the radius of that circle is half, correct? So now you see here, they have marked a 0 0.5 at the center, right? That point is nothing but 0 0.5 comma 0. Okay. And look at that r equal to 1 circle which is here, right? It has a radius equal to half. On both the sides it is half and half. So that's why that circle which where the r equal to 1 has been marked corresponds to a resistance equal to 1 circle. Are you okay with that? So this, so now if you look at the Smith chart, right, we have these kind of circles, right? All the circles will be meeting or they are touching each other at a particular point. That is the point corresponds to infinite resistance. Okay, open circuit, right? So the mark which I have marked with a dark dot here, that corresponds to resistance equal to infinity. Now you see, I can draw a horizontal axis that corresponds to the gamma r. Gamma r in the sense it is the real value of the reflection coefficient. Similarly, passing through the 0 point, I can draw a vertical line that will be my y-axis, that is the gamma I. Okay, so what is gamma I? Is the imaginary part of the reflection coefficient. So corresponding to every load, I have a gamma value, right? Corresponding to every load, I get a gamma L value, which is gamma real plus or minus j times gamma I. So the gamma R can be point marked along this, say 0.1, maybe here. The gamma I can be 0.2, so a point here. You see, this point corresponds to a specific gamma. Okay, that's a point which we can. All right, that's how the gamma can be used to that can be used to plot the points on the Smith chart. This is a part of the Smith chart we understand now. So if you consider a Smith chart, you can see these kind of lines. They are called as the constant resistance circles. All right, so because every circle has a fixed value of R. Okay, so I'll give a name here. So far we have not termed them. So this is constant resistance circuits. Okay, so far so good. Now what we do, we'll go to the next equation. All right, so the next equation is coming from the other part which we had left earlier. So I'll go back and I'll copy the equation, I'll come back and we'll continue. So that means I'm trying to look at this equation number 2. So from equation 1, we understood that I initially simply told that that's the equation of a straight line, but later on we proved that that's the equation of straight line. Now I'm going to make another statement. Even this equation number 2 is equation of a circle. Okay, but as of now, when we simply see that, we don't understand. Okay, so for that, we need to do again, we need to look at that mathematically, then only we'll be able to understand. Okay, so let me try to copy this equation. Sorry, it's not getting copied. Just a second. Okay, let me write the equation itself. It's not getting copied. So from 2, equation number 2, I'm trying to write that once again. That says that the imaginary part of the impedance, that is x, is given by 2 times gamma I divided by 1 plus gamma r squared minus 2 times gamma r plus gamma I squared. Okay, let's manipulate this so that we can try to get the equation of say circle. So what we can do is that let's first cross multiply. So that is x into 1 plus gamma r square minus 2 times gamma r plus gamma I square is equal to 2 times gamma I. All right. So first let us multiply them. That means this is x plus x times gamma r square minus 2x gamma r plus x into gamma I square is equal to 2 times gamma I. Let me do one thing. Okay, I think this step is not needed. I'll actually, I don't need this. What I can do, I'll try to erase this. Sorry, this step, without that step also I can do something. I can simply easily get answer without doing a tedious calculation. So what I do, I bring the x to this side. I'll keep the remaining terms there. 1 plus gamma r square minus 2 times gamma r. Gamma I square is equal to 2 times gamma I divided by x. Okay, this is easier. Okay, so this is 1 plus gamma r minus 2 times gamma r plus the gamma I square minus 2 gamma I divided by x equal to 0. Okay, now what I do, I'll try to add and subtract the 1 by x square so that I can bring a square term here. All right, so that is, let me try to write the, sorry, this is a gamma r square. Okay, let me write the proper square first. So that is gamma r square minus 2 times gamma r plus 1. So this is a perfect square. Okay, then I'll write the term which I will try to make a square now. So that is plus the gamma I square I already have minus 2 gamma I by x is also what I have. Okay, and in order to make it a perfect square, I need 1 by x square, and I subtract 1 by x square. Right hand side equal to 0. So you see that this thing I'll club, these three I'll club. So when you club the first three terms, what do I get? I get like this. This is gamma r. Is it plus 1? Sorry, it's minus 1. My mistake. Gamma r minus 1, a minus b whole square. Correct? And the second term is a square minus 2ab plus b square. It's again gamma I minus 1 by x the whole square. Correct? Equal to 1 by x square. This is equation number 5. I'm going to compare this with another, the same set of equation, like that is x minus a whole square plus y minus b whole square equal to equal to radius square. That was my equation 4, which we had written earlier. So that's why I said that equation which we started with is again a equation of a circle. Now we get to know that. So what is a? This implies the center a comma b is equal to, see the first one, that is a is always 1, correct? Comma, what is b? B is 1 by x. What is x here? X is the imaginary part of my impedance. Are you okay? Whatever you find as x there, take 1 by x. That will be your y coordinate. Now again, this is very clear that a is always fixed to 1. Okay, but the y value keeps on changing. Right? Are you trying to, are you able to get that? The center of the circle keeps moving about the line, right? X equal to 1. X equal to 1 in the sense a fixed to 1, right? So always a value is 1, right? So if at all this is the origin, right? This is the line a equal to 1. On this line always a equal to 1. Now, depending upon the x value, you can see that, right? My circle is going to change. Okay, B is 1 by x. And what is the radius? What is the radius of this circle which we are trying to write now? What is capital R? Compare 4 and 5. Center is equal to A comma B. And let me write, what is the radius? Radius capital R is equal to R square is 1 by x square. So R has to be 1 by x. Right? Perfect. Okay. Now let us look at the various possibilities. All right. Let me say that capital X is equal to, let me say the capital X is equal to, sorry, the small x value equal to 0, because everything is dependent on the x value only, correct? Right? So if x is equal to 0, what happens? What is the center? Simply put, x equal to 0. Center becomes 1 comma 1 by 0, right? 1 comma infinity, right? So the center of that particular circle will be on that line, but located at infinity. Okay, height is infinity. So if I have a line like this is the center will keep on moving and it will reach to infinity. At infinity, I have a point circle. So this particular line is there, right? This itself will be the circle, correct? Because it's located at the center is at infinity. That's why it looks like a straight line form, right? This radius is infinity. Okay, I'll show you. Anyway, I'll show you that. I'll bring a diagram later just to understand. Okay, so that means this is the case and the radius is equal to infinity. That's the first thing. Okay, now let's consider, say, x is equal to infinity. What is the center? What happens? What is the a comma b? Put b in the equation, put x equal to infinity. So anyway, a does not need any x, right? It's 1 only, but 1 by infinity is 0, correct? And what is the radius now? So radius of that circle should be 1 by infinity 0, correct? So we consider something like this. This is a equal to 1 on this line. So this is a 0. So this is 1. So you see it is 1 comma 0. So this is the point 1 comma 0. And on the 1 comma 0, I should mark a simple point because radius is 0, right? If the radius would have been 1, I might have written a circle like this. But now you see the radius is not there. Radius is also 0. It means it is the point itself, right? Whatever is the center, that itself is the circle. Is it okay? Okay, now take another case, something like, let's take x equal to 1. What happens to the center of the circle? First point is 1. Second is 1 by 1. So 1 comma 1. And the radius is 1 by 1. That is equal to 1. In the sense, mark along this vertical line, mark a point like maybe this is the, sorry, maybe this is the point 1 comma 1. That's a point. From there you draw a circle, correct? So like this. So that is the circle. Okay, corresponds to x equal to 1. Is it fine? Okay, all right. Now, so let's bring all the set of such circles which we have discussed now, right? Everything I'll try to bring it into one picture. I'm just copying another picture now and I'll paste it here so that that corresponds to the one which we were talking about. Okay. Okay. Now you look at this. Right. So the horizontal line, that is a red colored line, which is our gamma r line, that itself is going to be the circle corresponding to x equal to 0. Okay. Because that x equal to 0 circle has center located at 1 comma infinity over here, right? 1 comma infinity. On this line, it is x value is 1. 1 comma infinity is located very far, correct? So whenever it is very far, you will not be able to identify that, okay, the circle, there is a circular shape coming. It simply, I can understand that it is a straight line because I don't see any curvature as the radius is infinite. Correct? So that's what is the meaning of this. Then as you move away, you can see that radius, the r becomes 0.5. This is r equal to 1 circle, right? The one which we see, right? Uh, like this one. I'll change the color. So this circle is the radius equal to 1 circle. Sorry, x equal to 1 circle, right? And at this point, whatever we see here, right, a single point that is located, that corresponds to x is equal to infinity, right? So x is equal to 0, that is the horizontal line. X equal to infinity is a single point, right? So because of all these reasons, we call these circles as, there's a name for that, that is constant reactance. Constant reactance or constant x circles. So far we understood that, yes, this is how it's going to look like. And our uh, the plot which we are going to look after clubbing both the constant resistance and the constant impedance circuits, impedance circles, we will be able to visualize uh, something like this. Okay, I'll bring the Smith chart into place now. Okay, let me try to chart. The combination of the constant r and the constant x circles means we have a basic Smith chart in place. So let's look at that now. Okay, now let me identify the where do I find the constant R circles? Okay, the constant R circles, I can try to find them along, right? They are the complete circles which we can see, right? For example, let me just go back and identify how the constant R circles look like, right? There you can see the complete circles over there, right? So outermost circle corresponds to the short circuit, and the dot which is present on the at the point 1 is the R equal to 1 second. So let me try to slightly reduce the size. Still it is not coming. Okay, let me further reduce slightly and see whether I can bring. Yes, now we can see the complete Smith chart, right? So where is the short circuit corresponding circle? That is this circle, right? Okay, somewhere here you are able to see this is the outermost circle. Okay, so this circle, if you complete, so this is the one. Sorry, I might come coming inside. So you are able to see that, right? So this is the circle. If you complete, that is the one circle that we are talking about. That is resistance is equal to 0. R equal to 0 circle. Then let me go back and check where is the R equal to 1 circle. So R equal to 1 circle touches your 0 as well as the 1. The one circle which touches 0 as well as R equal to 1 is that. So let me go back and check. See, this is the central point. The one circle which touches this as well as this is that. So that is the R equal to 1. Maybe this is the circle. Yeah, you can see that there is a circle, right, underneath this red color. Okay, so that is a circle which is R equal to 1. You can note that they have written R equal to 1 here. So the value is written like this, right? That is the R value. What is the R value corresponding to this? Everywhere they have the values written over there, right? We can zoom and we can check that. Okay, that's the value of R. Okay, so we could identify that. Okay, these are the various R circles. Now, if I want to find out where is R equal to infinity, right, that should be at a distance of 1 from the center. So if this is 0, if this is 0, and the one which point is here, right, this point is R equal to, this is a point where resistance is equal to infinite. Open circuit point is that. So whenever I want to represent R equal to infinity, I will be considering that particular point on the Smith chart. Okay, right. Now, if at all I want to find draw, say R is equal to maybe, let's say R equal to 2, right? So what do? I'll find out where is the R equal to 2, right? I think R equal to 2 somewhere here. This is 2 written. So corresponding to that, if you draw the circle, right? So this is the circle that corresponds to r is equal to 2. Okay, so as I move away, r increases, r decreases, my mistake, sorry. R is 0 here. Okay, so at this point r is equal to 0. uh, right, corresponding to this point it is r equal to 1, so r should be 2 inside this, and r becomes infinity over here. So that's the point. I should remember which is the direction for resistance being equal to 0, resistance increases, resistance decreases, etc. I should be able to recall. That is one very important aspect everyone should remember if we have to solve the problems associated with this. Okay, so constant R circles, yes, we are able to find that. We are able to mark. Okay, now the next thing we studied is the constant reactance circle. So the center of the circle of these circles lie along the line, right? That is the along the gamma r equal to 1 line. So if I want to visualize that over here, the gamma equal to 1 should be a line like this. So I'll draw a line. It starts here and gets extended in this direction. You see, this is the gamma equal to 1 line. Okay, so I can even draw that line below. So see, this is the gamma equal to 1 line. The red line which we see. Now, in the sense, every circle that I'm going to draw will have the center on this line. Okay, that's the fundamental idea. Now, let us see. Let's go back and check where is the x equal to 0 line. X equal to 0 line is the horizontal line itself. Right? So, horizontal line means that they have already drawn, right? That is this line. So I'll draw another line here. So starting from this, see, they have drawn a line here, right? So this itself is the gamma r, real value of the gamma. Okay, so the vertical line is the one where the gamma equal, this is 0, right? So you see this point is something like our 0. So this is 1 point, correct? This point is 1. So gamma r equal to 1 corresponds to that vertical line which we have drawn. So on this line, we will find out the various centers. So one center which is at infinity will be corresponding to x is equal to 0. Right? X equal to 0 will have a point that is at infinity. I'll just put an arrow mark, 1 comma infinity. Sorry, I'll show that again. See, that is 1 comma infinity, which goes to infinity. If you have a point at infinity, I'm not able to visualize the curvature of that circle. So it's simply a straight line, which is this. Okay, so that is the curve. That's the circle. Now let's move to the other circle we need to find out on this. That is right. Okay, these lines, let's write. So when x is equal to 0, right, r equal to infinity, and the point is located at 1 comma infinity. Move to the next one. When x is infinity, it is located at 1 comma 0 with radius 0. 1 comma 0, where you identify 1 comma 0. 1 comma 0 is this point itself. 1 comma 0. So this point itself is for x is equal to infinity. All right, so we identified that as well, right? Let's move further. If at all the x is equal to 1, right? X equal to 1 means what? I have to find out the point. That point should be located at, let's see the calculation. At x equal to 1, it is 1 comma 1. And radius is also 1, right? So you can identify that as x is equal to 1 circle. It may not be very clear. So 1 comma 1. So you can see that there is a 1 comma 1.0 written here. Okay, 1 point comma 0. So this is the we will sorry. Now you see. Okay, there is a 1. Okay, there is a 1 comma 0 written. That means this is the circle. This is the part of the circle. Sorry, I'll try to draw neatly on that. Okay, so this is the point. This is the 1. So this is the curve which we are trying to plot. It's only a part of the circle that I can see. Okay, so actually this continues like this, but since it is not on our Smith chart, we are not drawing that. Okay, so we can complete a circle. Now we can see the center of that circle lies somewhere here. That is 1 comma 1. It's actually center is located on this vertical line itself. Okay, if you draw the complete circle, this is how it's going to look like. Right, center is 1 comma 1. Like that, you can see as you, so this is the at infinity I have x equal to 0. This is x equal to 1, which means I have to come down if x increases. Now you see x equal to 2 here. Okay, x equal to 5 here, x equal to maybe 10 here, and so on. As you can see, the center of the circle keeps on closing to this point, and at infinity this point reaches 1 comma 0. So these lines what you see are the constant x lines. X is positive, it is above, x is negative, below. So x equal to -1 is this circle, x equal to -2 maybe this, -5, -10, etc. Like that you can identify the various x. Okay, so various x constant x circles can be identified like this. So those are the constant r circles and constant x circles we have discussed so far. All right, before we start solving the problems based on the Smith chart, as a first phase, we need to learn how to mark the various points on the Smith chart. That's going to happen today first. Okay, so okay, let me bring the Smith chart once again. And now we'll try to mark the various impedance points on this. Okay. All right. On this, I want to mark the following points. And the points are like this. So let us consider that we have a characteristic impedance of the line. Say Z naught of the line is equal to 50 ohms. Right? So 50 ohms transmission line. Now we have to mark the following loads on this picture. Okay, so the first value of the load Z1 is equal to 100 plus J50. So remember, every calculation, everything happens in the normalized form. In the sense, I should divide that by the Z norm. Okay. So when you divide this by 50, this becomes 2 plus J1. Okay. So I should, so this means the value of small r is equal to 2. Okay. So I'll write clearly now. So value of the constant r circle is equal to 2 and the value of constant x circle is equal to 1. So I need to find out where is constant r equal to 2 circle, right? So r equal to 2 circle, as we know, this is the r equal to 2 circle. Okay. So anyway, I will not mark the complete circle. So that's what. So if it is positive, x is positive, I just have to look above this. Okay. Only in this region. This region corresponds to the inductive load. Okay. X is positive. If x is negative, you look at this, the lower. Okay. So now I can see that x is positive. I just have to look at the uh, top half of the graph. So in that, in the top half of the graph, I am supposed to look at the r equal to 2 circle. Where is the r equal to 2? Yeah, r equal to 2 I have already marked. Look at the x equal to 1 circle. So x equal to 1 circle is this one. Okay, so this is the x equal to 1 circle. Just to find out their intersection. Their intersection happens over here. This is the point. Okay, this point is what we can call as the a point that represents the impedance that is equal to 2 plus J1. Okay, so what is that point? It is the intersection of, I can see the 2 written here, that is r equal to 2. You can see over here, you can see different values written. They are corresponding to the x value. So I can see that x value is equal to 1, right? The intersection of those two circles I can identify over here. Okay, so let me mark them properly. So this is the point which we are talking about. I'll just mark it. So this is the point. That is Z1 according to our this thing, our questions. All right, let's move further. I want to mark, say Z2 is equal to 75 minus J100. So what do you do? This has to be divided by 50. Correct? When you divide this by 50, I'm going to get 1.5 minus J2. Right? So 1.2 is the value of R. So I can see that this is 2, this is 1. So between them, somewhere here, I have a 1.5 circle. 1.2, 1.4, 1.6. So this is the 1.5 circle, somewhere like this. Okay, that should be, I should be able to find out the intersection of that circle with what's the value, J2 minus J2. So since it is minus, I'm going below, right? So look at the J2. Where is the J2? This is 1, 1.2468. This is the 2. So this is the circle J minus J2 and 1.5 is this. So the intersection happens here. So that is the point which I'm supposed to mark now. Okay, so this is the point which I'm going to mark as Z2. Okay, right. Let's move further. Next, I want to mark say Z3 is equal to J200, purely imaginary, and it is inductive. So when you divide this by 50, this becomes J4. Okay, so let us try to mark the point. Only x equal to 4 circle I should identify. There should, this is actually, this is, you can see this is 0 plus J4, isn't it? In the sense, intersection of 0, r equal to 0 is the outermost circle. R equal to 0 and j equal to 4 is what I want to find. Okay, so j equal to 2, 3, 4. You see, this is the point I'm talking, because j equal to 4 is intersecting with this circle. This is the outermost circle, which is r equal to 0. Correct? So this is the point which is corresponding to, I'll write Z3. I hope it is clear, right? Then let's move to the next point. I want to mark another point. Say Z4 is equal to 150 ohms. When you divide that by 50, you are going to get that as equal to 3. So I just have to identify R is equal to 3. Okay. So R equal to 3 means it has to be, right? This, I can write this as 3 plus J0. J0, x equal to 0 lies on which circle? It is a circle whose radius is infinity. Correct? Which is a circle with radius infinity, that is the horizontal line. You can see that, right? This is the line which we are talking about. The horizontal line which I am drawing now is the one that corresponds to x is equal to 0. On that line, mark 3. R equal to 3 circle. R equal to 1 here, R equal to 2 here, R equal to 3 is this point. Are you okay? It is on the horizontal line. So that is the Z4. Okay. Let's move further. Then I want to mark another one, that is say Z5. Let me say this is equal to infinity. Infinity in the sense it is infinity plus J infinity. All right. So infinity plus J infinity, it's a single point on this particular Smith chart. That is the rightmost point that is present. Okay, so I know that that is over here. This is a point corresponding to Z5. Okay, let's move further. I also want to mark the point that is say Z6 is a 0, short circuit. Right? I can try to write this as 0 plus J0. So intersection of 0 circle R equal to 0 with intersection of X equal to 0. Isn't it? R equal to 0 is this outermost circle and X equal to 0 is this line. Wherever they intersect is the point. Correct? So that is the leftmost point that is present on the curve. So that is somewhere here. I can call this is the point corresponds to Z6. Okay, all right. Let's move further. The Z7 is equal to say simply 50 ohms. Okay, 50 ohms. This can be, when I divide by 50, it is simply 1. 1 means that 1 means it is 1 plus J0. Correct? J0 means it is horizontal line. 1 means R equal to 1 circle. R equal to 1 circle intersecting with the horizontal line is this point. Correct? This is the point. Because R equal to 1 is this circle. Intersecting with the horizontal line happens over there. Right? So that's why this point is the one which corresponds to Z7. Okay, then let's move further. I want to go for another point, say Z8 equal to maybe 185 minus J9. 900. Okay, can you tell me its normalized value? Divide both the numbers by 50 and give me the answer. Okay, 3.7, 18. Okay. So that means I need to look at the r equal to 3.7 circle first. Okay. So r equal to 1, 2, 3 here. Maybe this is 4. So 3.7 is approximately here. Since it is negative, I'm looking downwards. Okay, somewhere here. And 18. Yeah, x equal to 18, I need to find out. So you see that this is 1. This point corresponds to 2. This is corresponding to, sorry. This is corresponding to 3, right? 4, 5, 6, 7, 8, somewhere very close. This is maybe 20. So 18 comes somewhere here. Okay, approximate. All right. So once you can see the uh, if we are able to see that this graph is not very clear, right? So I'm just giving you an approximate position of the point. Okay. So approximately this comes somewhere over here. Okay, somewhere here we might get the point, that is Z8. So similarly, go for Z9, that is equal to 10 plus J20, right? It is not normalized. We need to normalize this. So divide that by 50 and get me a value. So 10 by 50, 1 by 5.2, I guess, correct? Plus, what is 2 by 5? 0.4. So let us try to find out this point. I need to look at r is equal to 0.2. Okay, 0.2 is this particular circle, and since it is plus 0.4, it has to be above. Okay, so 0.0, 0.1, 0.2, 0.4, and 0.2. I think this is the point, right? This is the point that is corresponding to Z9. Okay, let's try to find out one more. Z10 is equal to, this is 15 minus J35. Okay, convert this into the normalized format first. Zero point 0.3, yes. 0.3 minus J 0.7. So R is equal to 0.3, right? 0.2 was here. So this is a 0.3. I have to look downwards because I'm looking for negative value of X, right? So corresponding to that, the 0.7 is this, which intersects with this somewhere here, right? So this is the point, I guess. This is the point. Am I right? 0.3 and minus zero point 0.7. So that is, this is the point corresponding to Z10. Okay, so far, this is how the points are supposed to be marked by using the constant x and constant r circles. Okay, so in the upcoming session, we will try to use the gamma values as well to first find out the various parameters, like what is a voltage standing wave ratio. Okay, what should be the various parameters of the line. We'll try to solve those kind of problems first. Then we'll move on further to solve the problems that are basically intended to match the loads.